This video covers Newton's law of universal gravitation and Einstein's general relativity theory. The concept of force in Newton's mechanics is defined as the product of mass and acceleration. Newton was interested in applying his laws of motion to describe the movement of astronomical objects. For this, he had to come up with an expression defining the force between objects in space. This definition is what is called Newton's law of universal gravitation. According to Newton, every particle attracts every other particle in the universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. For two objects with masses m1 and m2 separated by a distance d, the gravitational force is equal to, where g is the gravitational constant. Although one can determine the acceleration of gravity on Earth, knowing the value of the gravitational constant would require measurements of the Earth mass and radius. Henry Cavendish was born on October 10, 1731 and died on February 24, 1810. He was an English natural philosopher and scientist who was an important experimental and theoretical chemist and physicist. He is noted for his discovery of hydrogen. Between 1797 and 1798, Cavendish conducted experiments using a torsion balance and determined g to be equal to. Newton's theory of universal gravitation is seen as the first unification theory in which the known gravitational forces on Earth are used to explain astronomical behavior. Newton's law of universal gravitation implies that gravity acted instantaneously on very distant objects. Newton himself was deeply uncomfortable with the notion of action at a distance that his equations implied. In 1692, he wrote,
"That one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that, I believe, no man who has in philosophic matters a competent faculty of thinking could ever fall into it."
Johannes Kepler was born on December 27, 1571 and died on November 15, 1630. He was a German astronomer and mathematician. He is a key figure in the 17th century scientific revolution, best known for his laws of planetary motion. Kepler's three laws state that the orbit of a planet is an ellipse with the Sun at one of the two focal points. A line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. The square of a planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit. Newton was able to use his theory and derive Kepler's law of planetary motion. Newton's gravitational law was very successful for about 200 years, being able to describe and predict the motion not only of objects on Earth but also objects in our solar system. However, there were signs of problems. Mercury, the closest planet to the Sun, has an orbit that cannot be successfully described by the universal law of gravitation. Both Galilean and special relativity rely on the concept of inertial frames of reference. Observers or objects that are accelerating require special treatment. Imagine a stationary observer on an inertial frame of reference based on x and t coordinates, and a moving observer on a non-inertial frame of reference based on x' and t' coordinates. The moving observer is traveling with relative velocity vr with respect to the stationary observer, and he is also accelerating. The relationship between the inertial and non-inertial frames of reference accelerations is the forces on both frame of references are not the same. The last term is a fictitious force that must be introduced to account for the acceleration between the two frames of reference. For instance, when we use the Earth as a non-inertial frame of reference, the fictitious Coriolis force must be included to correctly account for the description of objects interacting with the Earth. Let's imagine a rotating carousel and three observers. The first observer is hovering above the carousel. He is not rotating. He is considered the inertial observer. The other two observers, indicated by the yellow and blue dots, are at the edge of the rotating carousel. At a certain point, one of them tosses a red ball with a certain velocity v. From the point of view of the first observer, the ball follows a uniform linear motion depicted as the red line. According to the other two observers, the movement of the ball is a curve depicted by the black line. According to them, this change in trajectory is caused by a change of the velocity vector direction, or an acceleration. The Coriolis force is the fictitious force associated with this acceleration to correct the description of the trajectory as perceived by observers that are not inertial. Einstein was interested in extending his theory of special relativity to deal with the movement of objects in space. Therefore, the only force he was interested in was the gravitational force. For the problems he wanted to address, the electromagnetic, strong and weak nuclear forces were irrelevant. Einstein knew of the limitations of Newton's universal gravitational law and wanted to extend his special relativity theory to non-inertial frames of reference where objects or observers are accelerating. For this, he had to reinterpret the role of gravitational force and accelerations. In this process, he came up with an interpretation that the space-time frame can be curved. Before we venture any further on general relativity, let's see why it is so difficult for us to have an easy explanation for space-time curvature. A simple intuitive demonstration of the difficulties of us comprehending what a curved space-time looks like was presented by Richard Feynman. Feynman proposes to imagine we as two-dimension beings living on a purely two-dimensional flat surface. Since we are two-dimensional beings, we have no way of comprehending what a third dimension is. For all practical purposes, we only understand two space dimensions and time. Beings on this two-dimensional surface have been very successful in using Euclidean geometry to draw, build and measure things. They can construct straight lines, can measure angles, etc. For instance, they have been able to build squares and know that all angles of a square are right angles and all the sides have the exact same length. All worked fine for some time. At some point, when exploring their two-dimensional universe, they encountered very large squares with 4 right angles. But when they examine the sides of the square, they realize that one of the sides is shorter than the others. They are puzzled and confused. They measure everything very carefully, coming up with the same conclusion. Their universe does not follow the traditional Euclidean geometry on a larger scale. The solution to this problem came from another flat inhabitant of this surface universe. He came up with a new geometry called non-flat geometry and even provided equations to determine that this surface universe is distorted or curved, and this distortion can be measured by a curvature length that could be calculated from the large squares they were encountering. They were familiar with curvature of a line, but curvature of the flat space. What is that? According to this new non-flat geometry, if A is the length of the 3 equal sides of the square and B is the size of the shorter side, the surface curvature radius, a term that had no meaning for those flat beings, is determined as. Once this radius was determined for the universe, they could even estimate the shorter side length d for a square that had 3 other sides equal to c. This happened because the surface universe is not flat and is curved as a surface on a very large sphere. The squares those beings were encountering are similar to the areas enclosed by parallels and meridians on Earth. Although all those lines intersect at right angles, the closer we move away from the equator towards the poles, the smaller the distance is between meridians. On a small scale, close to the equator, squares on the sphere are very close to flat squares, and Euclidean geometry worked reasonably well. Once we understand that the two-dimensional beings can infer that their universe was curved and can determine equations to describe it, we wonder if we could do the same with our four-dimensional universe. Einstein's groundbreaking realization was that gravity is not a force at all, but is indistinguishable from, and in fact the same thing as, acceleration, an idea he called the principle of equivalence. He realized that if he were to fall freely in a gravitational field, such as a skydiver before opening his parachute, or a person in an elevator when its cable breaks, he would be unable to feel his own weight. But he also realized that if an astronaut in the cabin of a spacecraft that is accelerating upwards at the same rate as the gravity acceleration on Earth, the astronaut would not be able to discern if he was in an accelerating rocket or in a rocket standing still on the surface of the Earth. For instance, the feeling of his feet being glued to the ground just as they would be in Earth's gravity would be enough to convince the astronaut that the acceleration of the spaceship was indistinguishable from the pull of gravity on the Earth. Similarly, if he dropped a feather and hammer, both would hit the floor of the cabin simultaneously, exactly as would have happened if they had fallen on Earth under gravity. So, to Einstein, gravity and acceleration are equivalent. Imagine an observer inside a spaceship with walls that only allow the observer to see things inside the spaceship but not outside. Imagine light can pass through the walls in both directions without being modified. Imagine a second external observer stationary with respect to a light source. Imagine the spaceship is also stationary with respect to the light source. The observer in the spaceship does not know that, he only knows he is inertial. A beam of light enters and exits the spaceship. For the observer outside the spaceship, the beam of light followed a straight line path both outside and inside the spaceship. For the observer in the spaceship, he only detects that light follows a straight line path inside the spaceship. Now imagine the spaceship is still inertial but moving with a relative velocity with respect to the light source. In this case, for the external observer, the light follows a straight line path as indicated in the picture. For the observer in the spaceship, light also follows a straight line path, but to relate the path seen inside the spaceship from the point of view of both observers, we need to use the concepts of special relativity. Now imagine a third scenario where the spaceship and its observer are not inertial any longer. They are accelerating with respect to the light source. For the external observer, nothing changes and he sees the light still following a straight line path both outside as well as inside the spaceship. However, for the observer inside the spaceship, he will notice something curious. If he is able to determine the path taken by light at 3 points in time as shown in the picture, he will realize that they do not follow a straight line. They actually follow a parabolic path very similar to the path followed on Earth for a projectile. According to him, the acceleration of the spaceship has deformed or curved the space-time, creating this impression that light has been curved. Einstein realized that if this happens inside a spaceship that is accelerating, the same thing will happen with light when it passes close to a mass due to the equivalence principle. Therefore, without any further proof or data or experiment, Einstein moved forward with his derivation of general relativity, where light will still follow the shortest path between 2 points, but this path is now curved when in the neighborhood of masses. He went further and stated also that since due to the equivalence of mass and energy, energy can also curve the space-time. Christian Andreas Doppler was born on November 29, 1803 and died on March 17, 1853. He was an Austrian mathematician and physicist. He formulated the principle, now known as the Doppler effect or Doppler shift. He stated in 1842 that the observed frequency of a wave depends on the relative speed of the source and the observer. A common example of Doppler shift is the change of pitch heard when a vehicle sounding a horn approach and recedes from an observer. Compared to the emitted frequency, the received frequency is higher during the approach, identical at the instant of passing by, and lower during the recession. Imagine a stationary source emitting pulses at initial distance L0 from an observer. The observer is moving away with speed Vr in relation to the source. The pulses are being emitted at a frequency Fs, which corresponds to a wavelength or distance between the pulses at the source lambda s. The pulses travel at speed v. The receiving time Tr for a pulse emitted at time Ts at a distance L is given by. Now imagine one pulse emitted at time Ts0. It will be received by the receiver at a time Tr0 of. A second pulse leaves at Ts1 and is received at Tr1. The moving observer is now at position L1. Position L1 is determined as subtracting the first equation from the second equation and using the third equation for the relationship between positions L1 and L0, we obtain. Or the time difference between two successive pulses is equal to the period between the pulses. The period is inversely proportional to the frequency, and we can write or for the emitting and receiving wavelengths we have the wavelength and frequency arriving at the observer are then imagine an observer that is stationary and a pulse source located at a distance L0 from the observer. The pulse source is set up to start moving away from the observer with acceleration a after it sends a first pulse towards the stationary observer. The pulse travels with a velocity v. The frequency of the emitted pulses is Fs. The distance between the receiver and the emitting pulse source at time t is equal to the time it takes for the first pulse to be received is given by a second pulse is emitted at Ts2 and is received at Tr2. The relationship between the emitting and receiving times is so the time difference between the two pulses reaching the receiver is and the frequency as perceived by the receiver is related to the frequency of the emitting source by Up to here, all is very easy and clear. Einstein's geniality was to link this result with his principle of equivalence and say that clocks on a gravitational field will click differently than stationary clocks. Einstein predicted that clocks located at points apart in the direction of a gravitational field would register different times. His interpretation is that gravity is deforming or curving the space-time and the pulse's world lines are therefore distorted, resulting in the perception that there is an acceleration. There was no proof of this at the time. In fact, the proof of Einstein's earth-shattering association was only obtained later with the Pound-Rebka experiment in 1959. Einstein, who died in 1955, did not see this last confirmation of his theory. Clocks that are far from massive bodies, or at higher gravitational potentials, run more quickly, when compared to clocks closer to massive bodies, or at lower gravitational potentials. This effect has been demonstrated by noting that atomic clocks at differing altitudes, and thus different gravitational potential, show different times. The effects detected are extremely small, with differences being measured in nanoseconds. The effect is different than the special relativity time dilation due to relative velocity between frames of reference. The special relativity time dilation is symmetric because observers in inertial frames of reference perceives all clocks moving in relation to them as running slower, making the effect reciprocal. Whereas for gravitational time dilation, all observers agree which clock runs slower and which clocks run faster based on their relative position in the gravitational potential field. Marcel Grossmann was born on April 9, 1878 and died on September 7, 1936. He was a Swiss mathematician who was a friend and classmate of Albert Einstein. Grossmann came from an old Swiss family in Zurich. His father managed a textile factory. He became a professor of mathematics at the Federal Polytechnic School in Zurich, specializing in descriptive geometry. Grossmann introduced Einstein to tensor calculus and Riemannian geometry. Einstein and Grossmann worked together on a general theory which would unite special relativity with gravity. Their joint paper, Outline of a Generalized Theory of Relativity and of a Theory of Gravitation, which was published in 1913 and was one of the two fundamental papers which established Einstein's theory of gravity. Michel Angelo Besso was born on May 25, 1873 and died on March 15, 1955. He was a Swiss-Italian engineer. He worked very closely with Albert Einstein. Marcel Grossmann and Michel Besso were particularly important in helping Einstein develop his theory. But help came not only from collaborators, it came also from competitors. Several new theories had been proposed in which gravity, like electromagnetism, was represented by a field in the flat space-time of special relativity. A particularly promising one came from the young Finnish physicist Gunnar Nordström. Gunnar Nordstrom was born on March 12, 1881 and died on December 24, 1923. Einstein worked on both theories between May and late August 1913, with Besso making significant important calculations and pointing problems with the theory. In the summer of 1913, Nordstrom visited Einstein in Zurich. Einstein convinced him that the source of the gravitational field in both their theories should be constructed out of energy and momentum. Einstein concluded his comparison of the two theories with a call for experiment to decide. Einstein-Grossman theory predicts that gravity bends light, whereas Nordstrom's does not. It would take another 5 years to find out. Adriaan Daniel Fokker was born on August 17, 1887 and died on September 24, 1972. He was a Dutch physicist and was a former student of Lorentz. For the rest of 1913 and early part of 1914, Einstein worked with Grossman and Adriaan Fokker to reformulate the Nordstrom theory using the same kind of mathematics that he and Grossman had used to formulate their theory. It was clear that gravity could be incorporated into both theories as a curvature of space-time. However, Besso pointed out problems with the theory. David Hilbert was born on January 23, 1862 and died on February 14, 1943. He was a German mathematician and philosopher of mathematics and one of the most influential mathematicians of his time. By the end of 1914, the problem was attracting a lot of attention of many other physicists and mathematicians. In particular, Hilbert started working on the problem. Einstein rushed throughout 1914 and 1915, publishing a series of papers modifying the equations in the process, trying to solve the problems before Hilbert could come up with a solution. By November 1915, he published his final work on the general theory of relativity and for gravity field equations. Newtonian physics applied to the system of a single planet and the Sun predicts the planet orbit to be an ellipse with the center of mass of the system at a focus of the ellipse. The point of closest approach to the Sun, called the perihelion, is fixed. However, for the solar system with several planets, many effects cause perihelion to move or rotate around the Sun, a phenomenon called precession of the perihelion. The most important ones are the presence of other planets which perturb one another's orbit and the fact that the Sun is not a perfect sphere. When those effects are considered, Newtonian physics makes very good prediction of the solar system planets' orbits except for Mercury. The theoretical results were off by around 10% of the experimental measurements of the precession of Mercury's perihelion. Vulcan was a fictitious planet that was thought to cause the anomaly of Mercury's orbit but was never discovered. On a third paper that November 1915, Einstein used his theory, which included the curvature of space-time due to gravity, to fully describe the orbit of Mercury. This was the first test of Einstein's general relativity theory. Erwin Finlay Freundlich was born on May 29, 1885 and died on July 24, 1964. He was a German astronomer. Freundlich was a working associate of Albert Einstein. According to Einstein general relativity, the light from a star is deviated as it passes around the Sun. The Sun was too bright to allow any observation of the phenomena, but the idea was to carry those observations during a total solar eclipse where the Moon would block the Sun's light, allowing for the dim star positions to be determined and compared when they were not behind the Sun. Charles Dillon Perrine was born on July 28, 1867 and died on June 21, 1951. He was an American astronomer expert in solar eclipses, who moved to Córdoba in Argentina as director of the Argentine National Observatory. Freundlich contacted Perrine and asked him to include observation of light deflection as part of the Argentine Observatory's program for the solar eclipse of October 10, 1912 in Brazil. Perrine brought specialized equipment dedicated to observing light deflection. Unfortunately, the expedition suffered from torrential rains throughout the path of totality, which prevented any observations. Nevertheless, Perrine was the first astronomer to make a dedicated attempt to observe light deflection to test Einstein's prediction. Arthur Stanley Eddington was born on December 28, 1882 and died on November 22, 1944. He was an English astronomer, physicist, and mathematician. In 1920 he discovered that the mechanism of nuclear fusion of hydrogen into helium is the source of stellar energy. Arthur Stanley Eddington had taken part in a British expedition to Brazil to observe the 1912 eclipse but was interested in different measurements. Eddington and Perrine spent several days together in Brazil and may have discussed their observation programs, including Einstein's prediction of light deflection. William Wallace Campbell was born on April 11, 1862 and died on June 14, 1938. He was an American astronomer and director of Lick Observatory from 1901 to 1930. The solar eclipse of August 21, 1914 in Crimea presented another opportunity to determine whether gravity bends light. There were 3 expeditions working on the observations. The 3 directors were Erwin Finley Freundlich, from the Berlin Observatory, the U.S. astronomer William Wallace Campbell, director of the Lick Observatory, and Charles D. Perrine, director of the Argentine National Observatory at Córdoba. The 3 expeditions traveled to the Crimea in the Russian Empire to observe the eclipse. However, the First World War started in July of that year, and Germany declared war on Russia on 1st of August. The German astronomers were either forced to return home or were taken prisoner by the Russians. Although the US and Argentine astronomers were not detained, clouds prevented clear observations being made during the eclipse. Another eclipse on May 29, 1919 presented an excellent opportunity, because it would take place with the Sun in front of a bright group of stars called the Hyades. The brightness of these stars would make it easier to measure any changes in position. A joint committee between the Royal Society and the Royal Astronomical Society organized 2 expeditions. One was sent to the West African island of Principe and the other to the Brazilian town of Sobral. The Principe expedition members were Eddington and Edwin Turner Cottingham, while the Sobral expedition members were Andrew Crommelin and Charles Rundle Davidson. Both teams started observations with cloudy skies, but in Sobral, the sky cleared and the moon's disk began to obscure the sun shortly before 8:56 a.m. The eclipse lasted 5 minutes 13 seconds. The team remained at Sobral until July to photograph the same star field at night. The results were announced at a meeting of the Royal Society in November 1919, confirming Einstein's predictions. The superposition of the photographs taken at Sobral during and after the eclipse clearly shows the effect of the sun acting as a lens bending light. This picture shows the position of the stars farther away from the sun during the eclipse as compared to their positions closer to the sun in the July photograph at night. Robert Vivian Pound was born on May 16, 1919 and died April 12, 2010. He was a Canadian-American physicist who helped discover nuclear magnetic resonance, winning the Nobel Prize in Physics in 1952 for that discovery. He became a tenured professor of physics at Harvard without ever having received a graduate degree. Glenn Anderson Rybka Jr. was born on September 19, 1931 and died on January 13, 2015. He was an American physicist. The Pound-Rybka experiment monitored frequency shifts in gamma rays as they rose and fell in the gravitational field of the Earth. The measurement of gravitational redshift and blueshift by this experiment validated the prediction of the equivalence principle that clocks should be measured as running at different rates in different places of a gravitational field. Einstein's general relativity equation is: the right-hand side is the energy and momentum tensor. It describes how energy and momentum are distributed in space and how they flow from place to place. The left-hand side describes the structure of space-time and how it is curved, with the last term containing Einstein cosmological constant. Derivation of Einstein field equations is beyond the scope of this video. We will present a brief description of each term of the equation. Elwin Bruno Christoffel was born on November 10, 1829, and died on March 15, 1900. He was a German mathematician and physicist. He introduced fundamental concepts of differential geometry, opening the way for the development of tensor calculus, which would later provide the mathematical basis for general relativity. Gregorio Ricci Curbastro was born on January 12, 1853, and died on August 6, 1925. He was an Italian mathematician. He is famous for the development of tensor calculus. Einstein's general relativity equation is a tensorial equation. Space-time vectors have 4 components, 1 for time and 3 in each spatial dimension. The tensors involved are 4x4 tensors that describe 16 equations. However, the terms above the tensor diagonal are equal to terms below the diagonal. This reduces the number of Einstein's general relativity field equations to 10. We will start with the indices mu and nu. Those represent the 4 space-time coordinates. They can assume the value of 0 for time and 1, 2 or 3 for each of the spatial coordinates. Some of the terms we are already familiar. We already know what the metric tensor is. This tensor allows the determination of the space-time separation in Minkowski spacetime. A local Minkowski spacetime tangent to a gravity-curved spacetime general coordinates is used to represent infinitesimal spacetime separation, similar to how infinitesimal line distances are used to determine lengths along a curved path. The first term involves the Ricci curvature tensor. In differential geometry, the Ricci curvature tensor is a geometric object that measures the degree to which the geometry of a given metric tensor differs locally from that of ordinary Euclidean space, or the pseudo-Euclidean Minkowski spacetime. The second term involves the curvature scalar, or the Ricci curvature scalar are multiplied by the metric tensor. The Ricci scalar is a real number that measures the curvature of a surface. It is defined in terms of partial derivatives of the metric components and completely characterizes the curvature of a surface. The third term is the cosmological constant multiplied by the metric tensor. Einstein's publication of 1915 did not have this constant. It was added later in his work published in 1917 after realizing that the original equations imply a dynamic universe for which space is a function of time. He included a constant value that makes his universe static and eternal, which is known as Einstein's static universe. In 1931, Einstein accepts the theory of an expanding universe and proposes, in 1932 with the Dutch physicist and astronomer Willem de Sitter, a model of a continuously expanding universe with zero cosmological constant, known as Einstein-de Sitter universe. Later, Hubble proved that the universe is expanding and the cosmological constant was dropped. However, it was brought back into general relativity to include the effect of dark energy, since the no mass and energy of the universe could not explain the experimental data on its expansion. On the right-hand side, we have several physical constants multiplying the stress-energy-momentum tensor. The stress-energy-momentum tensor describes the density and flux of energy and momentum in spacetime. It is a generalization of the stress tensor of Newtonian physics. It is an attribute of matter, radiation, and non-gravitational energy fields. This density and flux of energy and momentum are the sources of the gravitational field in the Einstein field equations of general relativity. It requires auxiliary models to describe the equation of state for the contents of the universe. The terms on the left-hand side are all geometric terms that define the curvature of spacetime. The term on the right-hand side is related to mass and energy. This is as far as we will cover for Einstein general relativity field equations in this video. Wheeler's famous quote from his book A Journey into Gravity and Space-Time is a very good description of what Einstein general relativity equations mean.
Space-time grips mass, telling it how to move. Mass grips space-time, telling it how to curve. Einstein, with his geniality and with the help of many others, has shown how the universe works in large scales.